Hi, I'm Tony Heipel, and welcome to the Conceptual Git video series. When I started using Git, I was faced with a lot of terminology. Now, some of it I understood, but some of it really didn't make any sense to me. And I found that as I started using Git, I got a little more confused until I spent quite a bit of time with it and did a lot of studying on my own. Seems like it shouldn't be that hard, so the goal of this video is to actually help you build a conceptual model of Git using concepts you're already familiar with that make day-to-day use of Git seem a little less mysterious and obtuse. So let's start with some programming concepts. For those of you with any kind of computing background, one of the first data structures you learn is called a linked list. Now to review, a linked list is a data structure whose elements are nodes. Those nodes contain data and a pointer to the next node in the list. The linked list itself is just a pointer to the first node, the head, and this data structure can dynamically grow. Usually the very first data structure you learn is an array, and what we learn about an array is that it is allocated as a contiguous portion of memory, and that if you need to grow that data structure beyond its current bounds, you must actually create an entirely new array, copy all the data over, and then delete the old one. So the value of a linked list is that its size can continue to grow and change over time, and it is pretty efficient about doing so. Here is conceptually what a linked list looks like. Again, the linked list itself has a head that points to the first node, node 1. Then node 1 has a next pointer to node 2, and node 2 has a next pointer to node 3. If code is something that you prefer to see, here's a look at what a linked list looks like in code. In this case, it simply says that a node has a value and a next, just like we talked about, and this is in Java, and it is using generics. So the T just represents the value of the node. It could be an integer, a string, or any other object. Now, there are a couple ways to grow a linked list. The first we are going to look at is how to append a new node to the end of a linked list. To do so, you have a new node, and then you take a look at the linked list's head pointer, and you follow it until you hit the end of the list. Then you take that last node's next pointer and point it to the new element. It's pretty straightforward. So now let's say that in this case that you want to add node 4. You follow the same procedure, although this time you'll notice there's an extra hop. That's because node 3 exists in the linked list, whereas it didn't the first time. What this represents is something called an O of n operation. Again, a reminder, big O notation talks about algorithmic complexity, which is based on the number of things that you have in your data structure, or the number of items you're working on in an algorithm, how much time does it take to execute that? So in this case, appending a new node to a linked list is called a big O of n operation, which means that the algorithm takes longer depending on the number of elements in the data structure. There's another way to grow a linked list, which is inserting a new node at the beginning. Let's see how that looks. So here I have node 2 that I would like to insert at the beginning of the linked list. So again, we start with the head. We look at the current node that points to the head, and we simply point node 2's next node to the current head of the list, and then point the head to the new node. And if we were to iterate through the linked list, we would see that we would first visit 2 and then 1. So now 2 has been inserted at the beginning of the linked list. If we were to insert nodes 3 and 4, we actually see that it takes the same number of operations. It's two steps. We find the current head of the linked list. We point the new nodes next to the current head of the linked list. And then we point the head of the linked list at the new node. This is called an O of 1 operation. What this means is that no matter how big the data structure gets or how many elements are in it, it always takes a constant amount of time to do this operation. It might help to take a look at the code for these functions to see why that is the case. Now, as you can see on the left, we have the append function. And the interesting part of this with regards to big O notation and algorithmic complexity is the while loop towards the bottom. What that shows is it starts at the head of the list and loops through all of the elements of the list until it hits the end, and then sets the last element's next node to the new node. If you look at insert, however, not only is it shorter, but you'll see there's really only ever two steps regardless of the size. It simply checks to see if the head is null, and if it's not, it sets the new node's next pointer to the current head, and then moves the head to point to the new node. That's it, always two steps. That's why it's constant time. Now, why would linked lists apply to Git? Well, as you can see, I have here a linked list, but I've laid over the top of this Git terminology. Now, in this case, a node of the linked list is a type called commit, and its value is a value we are going to refer to as a commit value. New commits are always inserted at the head of the list. There is not an append. The next pointer is actually called parents. Now, while it's plural, we aren't going to deal with that now. We will see more about that later in this video. If you look at the branch, each branch is actually a linked list whose head reference points to the branch's head commit. So in this case, branch master is the linked list that starts with commit 4. And your working directory, which is the directory in which you make modifications to files, it has a head pointer, and it is just a reference that points to the current branch's head reference. In this case, the current branch is master, and head simply points to master. Given these applications of linked list terminology to Git, let's see how some common Git operations work. The first one we'll look at is git log. Now what git log does is it looks at your current working directory's head pointer, follows it to the branch, and then therefore the very first commit of that branch. And then it simply traverses the list and prints out the information of each commit along the way. Another common operation is that you've made modifications to some files in your working directory and you would like to commit those to the master branch. So in this case, you say that you add all of the files in the current working directory that have been changed. And what that command does is take and create a commit value, again, the value of a commit node. It takes the current working directory, creates a commit value, and adds it to a staging area. When you're ready, you commit all of the changes and the commit value that come out of those changes, and they go from the staging area into a new commit node. And that commits node is inserted at the head of the list following the same algorithms we saw earlier. Now notice, head didn't move, but if you ask Git what its head points to, it will say commit 5. That's because the master branch was moved to point to commit 5. Now let's take a look at basic branching and merging. This is an area that actually can cause quite a bit of confusion at first, and so we'll start with the most basic changes and move from there. Now in this case, you've been working in some code and you got a bug report. So you create a topic branch called bug1 to do your changes in. And what branch does is it looks at the current head and creates a new branch pointing to that same head. So in this case, you now have a new branch or linked list that just points to commit 4. So really, branch master and branch bug have the same commit history at this point. To be able to do work on your bug, you need to actually check out your new branch. All this does is change the head pointer to point from the master branch to the bug1 branch. You make your changes, and then you add them to the staging area so that you can commit them. Now, when you do the commit, you will see very similar activity as we saw in the previous slide, but what you'll see in this case is that bug1 is the branch that moved forward, and commit 5 is in the bug1 branch, but it is not in the master branch because master points to commit 4. So all of these branches are is really just pointers to commits, and those are the commits at the head of that branch. So now you've finished your bug fix, and you would like to merge it back into the main line and get it into the master branch. So first, since you want to do work on the master branch, you check out the master branch. Then you simply say that you want to merge bug1 into master. Now what Git is able to do is it takes a look at the history of both branches. And it finds that they actually share a common history, where master actually points to commit 4, as does bug1. And there are no other commits in that history that they don't share. So Git is pretty smart about this, and it decides to just move the master branch up to commit 5. And now your bug fix is on the master branch. This is what's called a fast-forward merge. Now, if you've used tools like GitHub, and you've tried to push something that you have not resolved into what would be considered a fast-forward merge, GitHub will actually reject that. And that is because the GitHub servers don't want to be responsible for doing merges, other than the most basic ones, which is moving these branch pointers around. Let's look at a more complex case. In this case, you still had the bug report, you created your bug1 branch, you made your fix, which created commit 5, but in the meantime, somebody else made a commit that we'll call commit 6 to the master branch. Now when you go to merge your bug fix into master, what's going to happen? Well, the steps are the same in terms of what you type into your command line or use in your visual tool. You check out master because you're making changes to master. You then say git merge bug1. Now here's where the interesting part comes in. Git does a lot of work to find what's called a common ancestor. And that is used in an algorithm called a three-way diff, or a three-way merge. And we won't go into the details in this video, but what you can see is that it is pretty obvious how to merge this back together, which is you need to merge the changes from commit 5 and 6 together, and Git uses commit 4 as a common ancestor to try to do its best job. So the changes are staged, and then a new commit is created called commit 7 that actually ties together the bug1 branch and the master branch. Commit 7 is called a merge commit. It was really just created in order to bring branch bug1 and branch master together. You'll also notice that commit 7 has multiple parents. We talked about that earlier, that the next pointer is called parents in Git. And in this case, you're actually seeing that there are multiple parents. This is no longer a linked list. This is now called a directed acyclic graph. So let's revisit our computer science classes. A directed acyclic graph, we can break it down just by looking at the words. All directed means is that the edges of the graph are directional, meaning they have arrows. And in all of our examples, you've seen that the nodes point to directionally another node. Acyclic simply means that no edges connect to nodes that create a cycle. So in our case, we are never going to have a node that points to another node that you could then basically go around in circles and get stuck forever. Git does not allow that. And then a graph is simply a set of objects and the connections between them. So if we take a step back, we can summarize all the concepts we've seen so far into three main objects. The first one is a commit, and again, it looks just like a specific linked list node where it has a value and a next node, or in this case, parents. For those of you not familiar with Java, an iterable is the equivalent of IEnumerable in .NET or enumerable in Ruby. It just means something you can iterate over. A branch looks just like the linked list data structure with one additional field, which is called a name. And a repo really just has a few small things in it. It has the current branch that you are editing. It has a list of all of the branches keyed by the name of the branch. So actually in this case it's a map, or a hash table is really another way to think about that, so that you can quickly access branches by name. And when you ask for the head of the repo in your current working directory, you can think of it as a function that just returns the current branch's head pointer. So to summarize, when we use Git, we're really just using a tool to create and edit a directed acyclic graph whose nodes contain some commit values and whose edges are their parents. That's really a powerful concept because most of the common Git operations that you're going to do, you're just moving pointers to commits around. There's really no magic to it. I want to take some time to thank Scott Chacon for his videos and specifically his Pro-Git book. That was a huge source of my understanding of Git, and thanks to the folks that made that book free on the internet. This is just the first video in an entire series of Git concepts and common workflows that I hope is going to be able to help folks have a mental model of Git that helps them understand what they're doing. Stay tuned for more videos.